Hello, in this last video for chapter 22, I would like to introduce you to two brand new reactions that are rather unrelated to the other reactions in this chapter. In fact, in some ways they are the opposite. Because let me remind you that we have been talking about electrophilic substitution on a benzene ring, and that's the nitration, the sulfonation, the various Friedel-Crafts reactions, and the halogenation reaction. That's electrophilic substitution on a benzene ring. In these last two reactions, we're going to be talking about nucleophilic substitution on a benzene ring. So let's remind ourselves about what the difference is. In electrophilic substitution, some carbon with a hydrogen gets substituted for some electrophile, and typically that's going to happen on a benzene ring. The electrophile could be a Cl+, could be an NO2+, could be an SO3H+. In other words, something positive is replacing a hydrogen. Let's review what is nucleophilic substitution. We learned a lot about nucleophilic substitution in a much earlier chapter. In nucleophilic substitution, you're starting with a halogen, that's chlorine, bromine, iodine, on a carbon, and some nucleophile, that is something with a pair of electrons and typically a negative charge, will replace the halide, and so you end up with a nucleophile attached. And of course, as a byproduct, what is it that's replaced in an electrophilic substitution? An H+. So it's exactly the opposite in many ways. First of all, you're replacing something positive, that is the H+, with something negative, that's the X-. You're replacing it with something positive, that's the electrophile, as opposed to something negative, that's the nucleophile. So in the last two reactions, we're going to talk about reactions, nucleophilic substitutions that happen on benzene rings. So if it's going to be a nucleophilic substitution, we need to start with a benzene ring that has a halogen. So let's just think about chlorobenzene, and it could be bromobenzene or iodobenzene. And if we react that with a typical nucleophile, even if it's a very good nucleophile, like let's say cyanide, we know that cyanide is a very good nucleophile. Does cyanide replace chloride on a benzene ring under normal conditions? And the answer is no. So typically we say, we've learned the rule that nucleophilic substitutions don't occur on benzene rings. And let's think about why that might be. First of all, what would the mechanism have to be? Well, we know of two mechanisms of nucleophilic substitution. They're called SN1 and SN2. If this were to be an SN1 mechanism, it would require the halogen to leave first and leave a carbocation at that carbon. In other words, we would have to have some intermediate in which there is no hydrogen at that carbon. The other hydrogens or whatever groups are on the benzene ring would still be there. But that kind of an intermediate is very difficult to form. That kind of carbocation is extremely unstable. Notice that's not a Whelan intermediate. That positive charge does not resonate into the benzene ring. And if you're not convinced about why that's true, try drawing a Whelan intermediate and see how it differs from this. This is not a good intermediate, and therefore no SN1 happens on benzene rings. The other possible mechanism for nucleophilic substitution would be SN2, and that requires that the nucleophile attack the backside of an alkyl halide and push out the halogen from the front side. Well, that's impossible on a benzene ring because, remember, this is all flat, it's in a plane, and there's simply no way for a cyanide or any other nucleophile to get in behind that chlorine. It would have to somehow burrow through the ring to do that. And so therefore we know no SN2. And that's why typically you don't do nucleophilic substitutions on benzene rings. However, in this video, I'm going to introduce you to two reactions that do appear to be nucleophilic substitutions on benzene rings, so they break the rule that I've just given you, that is, nucleophilic substitutions don't occur on benzene rings. However, when we look at the mechanisms, we'll see that they are really not typical nucleophilic substitutions. And what we're going to see is that there are actually two kinds. So this is really two completely different mechanisms, different reactions that happen under different conditions, but we're going to categorize them interestingly enough. The first one's going to be what's called addition, elimination, and the second one is going to be called elimination, addition. And parenthetically, this one, the elimination addition reaction, is sometimes referred to as a Benzine mechanism, and that Benzine with a YNE ending may give you a hint as to what the mechanism is going to be. Well, let's do this first one first. In an addition-elimination mechanism, you're starting with, as I said, an an aromatic ring with a halogen, and again I'm going to use chlorine just to be clear, but it could also be bromine or iodine. But it doesn't happen normally. It will only happen if you have two or more nitro groups, or in some cases other electron withdrawing groups, but works best with nitro groups themselves. And then we can in fact react it pretty much with any nucleophile we might want. For example, hydroxide works fine, cyanide works fine, SH- works fine, other kinds of nucleophiles. Let's just use hydroxide as an example. And what we find is that we get fairly smoothly and without too much difficulty a nucleophilic substitution happening on a benzene ring. Exactly what I just told you can't happen. It really only happens though if you have nitro groups in all three or at least two of the three ortho and para positions on the benzene ring. So 2,4-dinitro is fairly typical of that kind of reaction. So how does that happen? If it can't happen by an SN1 or an SN2, what is the mechanism for that reaction? Well, let's write it out here. And I'm going to use this exact reaction, but others similar to it would occur. Again, having nitro groups in various ortho and para positions. So here's the mechanism. Step number one, the nucleophile actually comes in and attacks that carbon, makes a bond between the carbon and the OH, just exactly as it would if this were an SN2 mechanism, but it's not SN2, and that's because the chlorine doesn't leave immediately. Instead, the hydroxide adds onto this carbon, the chlorine stays there, and this pair of electrons moves out onto that carbon next door. So we have what looks kind of like a Benzine Intermediate. If you look carefully at this, you'll notice that it has two groups on that carbon. The chlorine that was there originally and the hydroxide is added in the nucleophile. But instead of being positive, as is true for Benzine Intermediates, it's now negative. And just like a Benzine Intermediate, we could draw two more resonance structures for that, which I will go ahead and draw one of, and then you can imagine what the third one would look like. But again, if we have the chlorine and the OH on that carbon, move the pair of electrons constituting that negative charge down into here to form the double bond and move that pair out onto the para carbon. I think what you can see is that, and again these are resonance structures, and again notice that the negative charge in two of the three resonance structures resides on the same carbon with a nitro. Nitro being an electron withdrawing group. In fact, you can really draw another resonance structure for this in which the negative charge is out on the nitro group itself, and you can draw another resonance structure for this in which the negative charge is out onto the nitro group itself. That's a very good negative charge. As carbanions, remember this is now a carbanion because it's negative, as carbanions go, that's a pretty good one. And so that explains why nucleophiles can attack that carbon if there are nitro groups there. If there are no nitro groups there, the corresponding resonance structure is not good enough to stabilize that carbanion. Anyway, once that happens, then in the second step, it's quite easy to see that the negative carbon pair of electrons that you just made will just drop back in to reform that double bond and push the chlorine out. And we end up with the hydroxide on there and the two nitro groups on there. And we have ejected CO-, which is, of course, always the leaving group when you do nucleophilic substitution on an alkyl halide. So it's a fairly simple two-step mechanism. Notice that the two steps constitute addition, we're adding in the hydroxide, and then elimination, we're losing the chloride. That's why this mechanism is called an addition-elimination mechanism. Two steps, first one the nucleophile comes in, second one the leaving group leaves. So just for completeness' sake, how does that vary from an SN1 or an SN2 mechanism? So what happens in the SN1? The leaving group leaves first, and then the nucleophile attacks. What happens in an SN2? The leaving group leaves and the nucleophile attacks at the same time. What happens in this third type? The nucleophile attacks, and then the leaving group leaves. So it's all a matter of what order do those two things happen in. When does the nucleophile attack and when does the leaving group leave? Now let's look at the second of the two new reactions we're learning in this chapter. Specifically the one that I've referred to as the elimination addition reaction. So let me introduce the kinds of conditions under which that happens. Let's say we're starting with a chlorine on a benzene ring with a methyl group. Now the methyl group's not essential, unlike the nitro groups in the last reaction we saw, which are essential for that reaction to occur. The methyl group here is not really necessary. I'm just putting it on here as we do this reaction in order to show you something strange about the product that you get, and therefore a hint as to what the mechanism might be. Turns out if you take parachlorotoluene and you react it with extremely strong base, like for example sodium amide, or you could use very concentrated hydroxide under high temperature conditions. Now let's just look at sodium amide here, NaNH2. That's an ionic compound that we have seen several times already in organic chemistry. Remember, it's a positive sodium and a negative NH2. And what we find out is that we get what certainly looks like nucleophilic substitution on the benzene ring. You end up with the chlorine being replaced with the NH2 group. And of course the byproduct here would be sodium chloride. The sodium and the chloride would go off as a byproduct. But what's interesting and very weird about this reaction is it's not the only product you get. You also get some in which the NH2 group and the CH3 are meta to each other. Even though you started with a chlorine para, you end up with some where the NH2 group is para to the CH3. And of course, there is a hydrogen at this position, and there is a hydrogen at this position. So not only has the NH2 added on the wrong carbon, but somehow hydrogen has shifted at the same time. How in the heck does that happen? Well, it's going to involve yet another mechanism, neither SN1 nor SN2 nor the addition elimination mechanism we just saw a minute ago. Instead, it's going to involve what's called elimination addition. In the first step, here's the parachlorotoluene. And of course there is a hydrogen next door. I'm going to draw that hydrogen explicitly, even though it's always been there. I'm just drawing it on purpose so that we can compare what's going to happen. And we're going to react it with the NH2 negative ion. What is the property? What's the main property of the amide or the NH2 negative ion? It's a strong base. Okay, so what is it going to do? It's not going to attack that carbon initially. Instead, what it's going to do is pull off that hydrogen. That may not seem like a particularly acidic hydrogen, and it's not. It's really a very unacidic hydrogen. But it's strong enough to react with a very strong base, NH2. At the same time, it's going to drop in a pair of electrons in here and eject the chlorine at the same time. So it's doing what is essentially an E2 elimination. Remember, that means the base comes in, pulls off the H+, drops in a pair of electrons, and ejects the halogen all at the same time. So after that's done, what do we end up with? We end up with the benzene ring. Methyl group is still there, unaffected, but now we have yet another pair of electrons in this bond. So I've drawn it with the resonance structure such that that's a double bond in here, and that's a double bond there. You could draw another resonance structure for that in which the three are just rotated, but it's typically done so that you get, so it looks like a triple bond there. Okay. And what's the byproduct of this step? Well, the NH2, having pulled off an H+ from here, gives ammonia. Now that is a very strange looking intermediate, this thing right here. And the reason I say that is because you have a triple bond, no hydrogen on this carbon, no hydrogen on that carbon. There are hydrogens, of course, at the other positions, and in this particular case, there's the methyl group right there. This intermediate is what's known as a benzine intermediate. Not too surprisingly, what it means is that there's a triple bond as one of the bonds of a benzene ring. Now that's not a typical triple bond. It really isn't sp hybridized at either of those carbons, as you might expect it would be if it was really a triple bond. Instead, it's more like a diradical, in which that's not really a bond, but really two unpaired electrons on there, or perhaps it's a negative on one and a positive on the other. It's really kind of unclear as to what the exact structure of that is, but it sure acts as if it's a triple bond. Then, in the second step of the benzine mechanism, whatever it was you produced as a byproduct in the first step comes back and adds on to where the triple bond is. So let's redraw that benzine. And now if we're going to take the ammonia and add a hydrogen to one of these and an NH2 to the other, essentially we're adding ammonia across that triple bond. Now ammonia doesn't typically add to triple bonds, but in this case it does because that's a highly, highly reactive triple bond. Should we have the hydrogen here and the NH2 there, or vice versa? And the answer is there's really no reason why either one of those would be preferred. So you get about equal amounts of some where the NH2 adds on there and the hydrogen adds on there, and some where the NH2 adds on here and the hydrogen adds on there. Really no reason why either one of those is any better than the other one. So therefore you get both, in fact, and that explains why we get both of those products in this particular reaction. Which mechanism, again, we are referring to as elimination, because we're eliminating these two to get a triple bond, and then addition, because we're adding these two onto a triple bond in either of the two orientations. So this is the elimination-addition mechanism, as opposed to the previous one, which was addition and then elimination. So really there are now 4 mechanisms we've learned from nucleophilic substitution: SN1, SN2, addition-elimination, and elimination-addition. The last one is always referred to as a benzine mechanism because one of the intermediates looks like it has a triple bond in a benzene ring. Let me give you one more example of this, see if you can predict what the product or products would be. Start with the same starting material, a chlorine and a methyl group. And this time we're going to use fused KOH. Well, what that means is that we're taking this material and we're putting it directly into solid potassium hydroxide and we're melting the whole thing. So no solvent, just plain, straight old potassium hydroxide. That's an extremely basic mixture because it's about as concentrated hydroxide as you can get with no solvent there at all. So we're going to fuse all of this. After we've, essentially that involves putting in a lot of heat because you're essentially trying to melt an ionic compound. But once the reaction is done, then we dump the whole thing into water, the product comes out, and what products are we going to get from that reaction? I use the word products because in fact there's going to be 2. I'll give you a chance to see if you can figure out what the products are going to be. Welcome back. We are going to replace the chlorine with an OH. The nucleophile in this case is the hydroxide. So the obvious product here is that product, but it turns out you get about equal amounts of that product. And again, it's because the hydroxide acts as a strong base, pulls off a hydrogen along with the chlorine to form a benzine at that position, and then the resulting water adds back in again, hydrogen versus OH or hydrogen versus OH, and we get both of those products. Again, just to review, we've learned 2 new reactions in this video, both of which are so-called nucleophilic substitutions on benzene rings, but they both occur only under very special conditions. The first one requires various nitro groups on the benzene ring in ortho and para positions, and the second one requires an extremely strong base or extremely concentrated form of a regularly strong base, and then you end up getting sometimes 2 products. Notice in this case, if the methyl group weren't there, you would still get the 2 products, but they would be the same as each other, and you wouldn't be able to tell that you in fact had done it through a benzine mechanism. That will finish this video. Thank you for your attention.